Hello, and welcome to the second presentation related to torsion of circular cross-sections. In the previous presentation, we reviewed simple torsion theory and derived what's termed the simple torsion equation or simple torsion formula. So in this presentation, we'll now apply our theory to solve some practical orientated engineering exercises. It is suggested you've seen the previous presentation related to the introduction to torsion theory before reviewing this presentation. Here's a brief overview of the presentation related to simple torsion theory and various worked exercises. We commence with a brief recap of simple torsion theory and the simple torsion equation derived in the previous presentation. Appropriate unity brackets are stated, for example, for conversion between revs per minute and radians per second. The table of section properties is included to calculate, for example, polar second moment of area for solid sections or for circular hollow sections. Example 1 is included, in which we use simple torsion theory to calculate the applied torque T and the angle of twist theta. And example 2, where we have to calculate the power that can be transmitted, simple P, for a given scenario. Exercise 1, for a given power P transmitted, we have to calculate the resulting angle of twist theta. Exercise 2, we undertake a comparison between a solid and a hollow circular section shaft. The comparison is regards to the torque and the mass or the weight of the respective shafts. Finally, in this presentation, exercise 3, we're given an angle of twist theta and we have to calculate the maximum and the minimum shear stresses in the shaft. Symbol tau for shear stress. And here are the approximate timings related to the commencement of each of the sections contained within the presentation, hopefully to aid your ease of access through the presentation. But please note these are only approximate timings. So simple torsion, overview. We're going to consider a circular section bar that's made from an elastic material and subject to an applied torque T as shown in figure 1. Here's figure 1 here, applied torque T. Such circular sections are used for shafts of electric motors or car engines. These are members subjected to torsion. Such a bar or shaft configuration can be analysed in simple torsion by employing the following, which is known as simple torsion theory. So from the previous presentation, we derived the equation T upon J is equal to tau upon R is equal to G theta upon L. We'll define these terms very briefly on the following slide. Just repeated the simple torsion theory equation here. So capital T is the torque applied in Newton meters. Capital J is the polar second moment of area, having the unit meters to the 4. And the Greek symbol tau is the torsional shear stress, having the unit of Newton per meter squared. Lowercase r is the distance from the center of the section or shaft to the fiber under stress, and r is in meters. Capital G is the shear modulus, also termed the rigidity modulus, and that's in newtons per meter squared. Theta is the angle of twist in radians, and L is the length of the bar or shaft in meters. Just note for reference, GJ, in other words the shear modulus multiplied by the polar second moment of area, is sometimes referred to as the torsional rigidity. Theta divided by L is sometimes referred to as the torsional stiffness. We will also make use of the equation torque is equal to force multiplied by radius. And torques are in Newton meters, of course. So that's an overview of the nomenclature and definitions of the various quantities of the simple torsion equation. Torsional shear stress distribution. So for bars having circular cross sections, the torsional shear stress distribution is as shown in figure 2. That's for a solid section. And in figure 3 for a hollow section. We reviewed these torsional shear stresses in the previous presentation. And for reference, I've shown here a list of unity brackets that will help with various conversions that occur within the problems we're going to solve. I've shown 3 specific unity bracket conversions here for reference, and a further 2 conversions shown here. If you need a recap on how to use cancelling unity brackets for such conversions, there's a separate presentation you can review. Let's consider the elastic polar section modulus. The value J divided by capital R is called the minimum polar section modulus, denoted by the symbol Z. ZP minimum is the J divided by R. To find the maximum shear stress, that would be the applied torque divided by the minimum polar section modulus. And it's often the value of the maximum shear stress in a shaft or a circular bar that we're interested in calculating. Let's consider circular section properties. Table 1 below lists section properties of solid and hollow circular sections. So here is the polar second moment of area J for a solid circular section. We outlined the proof to this in the previous presentation. And here is the minimum section modulus for, again, a solid circular section. Here is the polar second area moment for a hollow section shaft having external diameter capital D and internal diameter lowercase d. And again, the minimum polar section modulus is also stated. We'll refer to these section property calculations as required within the following exercises. Let's first consider an example. Example 1 here. We have a round bar of 125 millimeters diameter is to be used as a shaft. We're asked to find the maximum allowable torque, that's capital T in our simple torsion equation, that can be applied to the shaft if the torsional shear stress is to be limited to 18 newtons per millimeter squared. We're also asked to calculate the angle of twist, symbol theta, if the shaft length is 2.33 meters. We're given for reference the material's modulus of rigidity, that's the shear modulus capital G, 77 kilonewtons per millimeter squared. Obviously within this question we'll be using the simple torsion equation stated in the bolded box here for reference. From the question we're given the diameter, so that will allow us to find the J value if we need it, and also the R value. Usually it's the maximum R value, capital R, we're interested in. We're given the allowable torsional shear stress. So straight away I can see, using the first 2 parts of the simple torsion equation, I can find the maximum torque we can apply. And then knowing in the question we're also given the modulus of rigidity and the lengths of the shaft, I can use these 2 parts of the simple torsion equation to find the angle of twist theta. So if you think you can attempt example 1 without further assistance, I would encourage you to start the presentation and attempt it now, but I'll show you the full work solution on the following slides. So example 1, here's our solution. I've just listed the simple torsion equation here for convenience. So extracting the information in the question, we're given the outside diameter of the bar, 125 millimeters, capital D here. So that means I can find the maximum radius of the bar, 62.5 millimeters in this case. We're given the torsional shear stress, 18 newtons per millimeter squared. And we're given the length, capital L of the shaft, 2,330 millimeters. As we have already stated, the maximum radius is the diameter divided by 2, so 62.5 millimeters. And I can now calculate my polar second moment of area, capital J, from the equation for a solid shaft. It's pi d to the 4 upon 32. So inserting my diameter given in the question, that's 24 times 10 to the 6 millimeters to the 4. So there's our information extracted from the question. Example 1, solution continued. So part 1, as I've labelled it here, let's calculate the maximum torque. So from the above simple torsion equation, I'm using these two parts. And I simply transpose for torque capital T, multiply both sides by J in this case. So torque multiplied by J divided by R is the rearrangement. Inserting the values, that becomes 18 newtons per millimeter squared multiplied by 24 times 10 to the 6 millimeters to the 4, or divided by the radius here of 62.5 millimeters. So for the given parameters, the maximum torque we can apply is 6.92 times 10 to the 6 Newton millimeters, or divided by 1000, that's 6.92 times 10 to the 3 Newton meters. Considering part 2 here, I'm going to calculate the angle of twist, that's theta of the shaft. So now using these two parts of the simple torsion equation, so rearranging for theta, that's tau multiplied by L divided by GR. Again, inserting the values that were given in the previous slide, that evaluates to an angle of twist theta of 0.0087 radians. Note the angle is in radians. In this case, I've converted the angle to degrees using our standard conversion. So theta in degrees is theta in radians multiplied by 360 degrees divided by 2 pi. So that evaluates 2.5 of a degree. Example 2. We're asked to determine what is the power that can be transmitted by a solid shaft of diameter 100 millimeters, rotating at 5 revolutions per second, if the shear stress must not exceed 60 meganewtons per meter squared. To solve this problem, again we will need the simple torsion equation as used previously, but also now we will need the power equation of P is equal to T omega, which we outlined in the previous presentation. If you think you can solve this problem without further assistance, I would encourage you to do so. The answer is shown in the bracket here. The full worked solution is shown on the following slides. Example 2, solution. So extracting the information from the question, the angular velocity is 5 revs per second. To calculate omega in terms of radian per second, that's 5 revs per second multiplied by 2 pi. Gives me an angular velocity of 10 pi radians per second. The shaft diameter, D, is given in the question, 100 millimeters. I'm going to state that in meters because the shear stress is stated in terms of meganewtons per meter squared. So my shear stress, my shear strength here, 60 times 10 to the 6 newtons per meter squared. Obviously the maximum radius in this case, R, is half the diameter. So 0.05 meters is the maximum radius. That's R in our diagram here. Example 2, solution continued. Just thinking through the problem for a moment. Ultimately, we have to calculate the power P transmitted. We have the angular velocity calculated on the previous slide, but the torque T is unknown. So from our simple torsion equation, we need to find T, and we know from the information given the maximum shear stress we're allowed, we're given the diameter, so we have the maximum radius. And if we can calculate the J, which of course we can, well, we can then solve for the torque. And from there, find the power. So let's calculate the polar second moment of area, the J. For a solid section shaft, that's pi d to the 4 divided by 32. Our diameter is 0.1 meters, so J evaluates to 9.817 times 10 to the negative 6 meters to the 4. Next, we'll calculate from the simple torsion formula above the torque T by rearranging the first two parts of the simple torsion equation. T is equal to the shear stress multiplied by J divided by the maximum radius. We know the torsional shear stress is 60 times 10 to the 6 newtons per meter squared. We've just calculated the J value above. And of course the maximum radius is 0.05 meters. So the torque evaluates to 11,781 Newton meters. Now we're in a position we can calculate the power transmitted. Power is equal to the torque calculated above multiplied by the angular velocity from the previous slide. Inserting the values, the maximum power transmitted is 370.1 kilowatts. Let's consider some tutorial exercises. Here's exercise 1. We're asked to calculate the twist in degrees of a solid shaft having a diameter of 300 millimeters and 6 meters in length when it's transmitting 1.6 megawatts at 75 RPM. We're given the modulus of rigidity as 80 giganewtons per meter squared. So let's think through the solution for a moment. What are we asked to find in the question? The angle of twist in degrees. So we're trying to find angle theta. It will be in radians when we calculate it from the simple torsion theory here. We can convert that to degrees thereafter. What are we given in the question? Well, we're given the shaft diameter. So from that we can find the polar second moment of area. And of course we can find the maximum radius, half the diameter. We're also given the length in the question, 6 meters in length. Also from the question, we're given the power that's transmitted, 1.6 megawatts, so that's the P in this equation. And we're given the speed of rotation, 75 RPM. We will need to convert that into radians per second, but that does allow us to find the omega value here. And we're also given the modulus of rigidity, the G value. So from the left-hand equation for power, I can see we can transpose that to make the torque T the subject. We can calculate the value of torque T and place that into our simple torsion formula here. So we now know T. And then we can use these two parts of the formula here and here and transpose the equation to find theta. So that's our thought process through the solution. If you think you can attempt the question from here without further assistance, I would encourage you to do so. The answer in degrees is shown in the bracket here, but I'll show you the full work solution on the following slides. So exercise 1, beginning of the solution. As always, extract information from the question. We have the shaft diameter given in the question of 300 millimeters, but notice because the modulus of rigidity, this G value here, is in giganewtons per meter squared, that's the G value stated here, I'm going to convert my dimensions into meters to prevent any unit conflict. So in this case, the diameter is 0.3 meters. The length of the shaft is 6 meters, so L is 6 meters. The power transmitted is 1.6 megawatts, so capital P here, 1.6 times 10 to the 6 watts. And then the angular velocity is 75 RPM, so converting 75 RPM into radians per second, multiplied by 2 pi upon 60. So omega is 7.854 radians per second, 2 3 decimal places there. I have stated the maximum radius, which of course is half the outside diameter, but that's not actually required in this particular case, as we're not asked to find the shear stress in the shaft. Exercise 1, solution continued. So firstly, to calculate the torque, so from the equation P is equal to T omega, we can rearrange the equation to find the torque. That's P divided by omega, inserting the value for power and for angular velocity from our previous slide. That evaluates to a torque of 203.7 times 10 to the 3 Newton meters. Next, we're calculating the polar second moment of area, that's the J symbol, and for a solid circular section, we know that's pi d to the 4 divided by 32. Inserting our diameter in meters here, J is 792.5 times 10 to the negative 6 meters to the 4. From our simple torsion formula, we can now rearrange to find angle theta. So I'm going to use these two parts of our simple torsion formula. And to rearrange for theta, I simply multiply both sides by L and divide both sides by G. So L times T divided by G times J would evaluate theta. Inserting the L, the T, the G and the J into our equation, that evaluates to a theta, angle of twist, of 0.0193 radians. Remember that the simple torsion formula always yields radians for angle of twist. Finally, to convert from radians to degrees, our angle in degrees will be the angle in radians calculated above, multiplied by 180 divided by pi. So from that calculation, the angle of twist is 1.1 degrees to 1 decimal place. Exercise 2. A shaft used in an aircraft engine has a diameter of 50 millimeters. We're asked to find the maximum torque that can be applied to the shaft if the maximum allowable shear stress is limited to 84 meganewtons per meter squared. If the shaft now has a 25 millimeter diameter hole bored concentric with the shaft's circumference, we've got to calculate the percentage reduction in both the applied torque and the mass of the shaft. So again, before we commence the question, let's just think through the potential solution here. We're given in the question, we're given the diameter of the shaft, so we can calculate the polar second moment of area, and we can calculate the maximum radius. We're initially trying to determine the maximum torque, T, that can be applied, and we're given the shear stress that the shaft can withstand. Straight away I can see I'll be using these two parts of the simple torsion formula to calculate the applied torque T. We then have to determine the maximum applied torque to the hollow section shaft. As always, if you think you can attempt this question without further assistance, I'd encourage you to do so. The various answers are shown in the bracket, but I'll show you the full work solution on the following slides. Exercise 2, the solution. So extracting information from the question, we've got the shaft diameter, 50 millimeters. Again, as in previous problems, I will convert my dimensions into meters because the allowable shear stress stated here is in newtons per meter squared. Shear stress here is 84 times 10 to the 6 newtons per meter squared. So as I say, I'm going to put my diameter, capital D, in terms of meters here, 0.05 meters. We're also given the inside diameter of the hollow section shaft, little d here, again in meters, that's 0.025 meters. And for reference, I've calculated the maximum radius, that will actually be capital R on our diagram. That's the outside diameter divided by 2. So in this case, that's 0.05 divided by 2, that's 0.025 meters. So that's extracting the information from the question. Exercise 2, solution continued. So part A, let's consider the solid shaft. Let's first calculate the polar second moment of area for the solid shaft. We know the formula for J for a solid circular section is pi d to the 4 upon 32. Our outside diameter is 0.05 meters. So evaluating J for the solid section shaft is 0.6136 times 10 to the negative 6 meters to the 4. So now from our simple torsion formula, we're going to calculate the applied torque T. So essentially we're considering these two parts of our simple torsion formula, rearranging for T, in other words multiplying both sides by J. The torque allowed is the shear stress given in the question, multiplied by the J value above, divided by the maximum radius. Inserting the values, the maximum torque that the solid circular section can withstand is 2062 Newton meters. Let's now consider part B here, which is the hollow section shaft. Again, working out the polar second moment of area for the shaft. Formula for J now is pi multiplied by, in brackets, the outside diameter raised to the power of 4 minus the inside diameter raised to the power of 4, or divided by 32. Inserting the outside and inside diameters. That evaluates to a J value of 0.5752 times 10 to the negative 6 meters to the 4. And again from the simple torsion formula, rearranging for T, same process as above, and inserting the numerical values, we have a maximum torque that can be applied of 1933 Newton meters. So exercise 2, the solution continued. Next, consider the percentage reduction in torsional strength. So that will be the torsional strength of the hollow section minus the torsional strength of the solid section, all divided by the torsional strength of the solid section shaft. That evaluates to a reduction in torsional strengths of the hollow section compared to the solid section of 6.3%. Let's next consider the percentage reduction in mass or weight, and we know that this is relative to the change in cross-sectional area between the hollow section and solid section shaft. Exercise 2, solution continued. Just show you that relationship here. This little calculation relates to whether the shaft is a solid section or a hollow section. I'm considering the weight here. The weight of the shaft is the material's mass density multiplied by the volume of the shaft multiplied by gravitational acceleration. In symbol form, that's W is equal to rho, Greek symbol, multiplied by the volume V multiplied by gravitational acceleration G. However, we notice that the volume of the respective shaft is the cross-sectional area multiplied by the length of the shaft. So V can be replaced with A multiplied by L. What we notice now when reviewing this equation is that the mass density rho, the length L, and the gravitational acceleration G are all constants, which I'm going to call that single constant K. So the weight force actually equals to K multiplied by A. In other words, we write that the weight force, or the mass in our particular case, is proportional to the cross-sectional area. So to evaluate the percentage reduction in the mass for the solid section shaft, labelled A1 here, the cross-section area is calculated from pi d squared upon 4, inserting the outside diameter, and evaluating area 1 is 0.00196 meters squared. Now evaluating area 2 for the hollow section shaft, using the formula for the cross-sectional area of a hollow section, inserting the outside and inside diameters, and evaluating area 2 is 0.001473 meters squared. So to calculate the percentage change in weight or mass, it's the cross-sectional area of the hollow section minus the cross-sectional area of the solid section, all divided by the area of the solid section. And that evaluates to a reduction in mass of 24.8%. So we can now see in this particular instance, by boring out the centre of the shaft, we reduce the torque that can be transmitted by approximately 6%, but we reduce the mass or the weight of the shaft by approximately 25%. Exercise 3. A steel tube 10 mm outside diameter and 6 mm inside diameter has a length of 4 meters. One end of the tube is gripped firmly and the other end is twisted through an angle of 30 degrees. If shear modulus G for the steel is 80 kilonewtons per millimeter squared, we're asked to calculate the maximum and minimum shear stress in the tube and the torque required. For your reference, here's the simple torsion formula. I'd encourage you to think for a moment how you're going to use this to calculate the maximum minimum shear stresses and then the torque required. I'd encourage you to stop the presentation and attempt this question. The answers are shown in the bracket here. And I'll show you the full work solution on the following slides. Exercise 3, solution. Just notice in this question, because the modulus of rigidity G is stated as 80 kilonewtons per millimeter squared, I will now ensure all my dimensions are in meters. And again, to prevent any unit conflict from occurring. So my outside diameter of the shaft is 10 millimeters, stated in the question. Inside diameter, lowercase d, here is 6 millimeters, that's stated in the question. But notice that the length is 4 meters in the question, so I've converted that to 4,000 millimeters here. We're given in the question the angle of twist is 30 degrees, so theta is 30 degrees, and I've converted that into radians here. G value we know is 80 times 10 to the 3 newtons per millimeter squared, and I've determined the maximum radius R of our hollow section tube here. That's obviously the outside diameter divided by 2, so that's 5 millimeters, and also of course calculated the minimum radius, which is the inside diameter, lowercase d, divided by 2, so 3 millimeters, so little r here is 3 millimeters. Exercise 3, solution continued. Obviously the first thing we need to do is to calculate the polar second moment of area, J, for a hollow section shaft here. Evaluated as 854.5 millimeters to the 4. And then using these two parts of the simple torsion formula, I'll rearrange for shear stress, and I'll first of all calculate the outside shear stress, labelled as tau O. Transposition here, multiplying both sides by little r, so that's G multiplied by theta multiplied by the outside radius r divided by length L. Inserting the values, the outside shear stress is 52.4 newtons per millimeter squared, and a similar approach to calculate the shear stress at the inside radius, labelled tau I here. Same equation, but this time we're using the lowercase r, the inside radius, 3 millimeters. That evaluates to 31.4 newtons per millimeter squared. I just showed you an alternative way of calculating the inside shear stress, and that's based on the linear stress relationship of the shear stress across the section, something we reviewed in more detail in the first presentation. This method also evaluates the internal shear stress as 31.4 newtons per millimeter squared, which of course we'd expect. That's just an alternative calculation purely for reference. Exercise 3, solution continued. And finally, we're asked to calculate from the simple torsion formula the torque required for this particular angle of twist. So now I'll be using these two parts of the simple torsion formula, multiplying both sides by J to find T. So T is equal to G theta J divided by L. And again, inserting the values, the torque required to give the 30-degree angular movement in this exercise is 8,955 Newton millimeters. Just note, as always, the value of theta used in the simple torsion formula must be in radians. That's 0.524 radians there. And here's the bibliography used to help generate the presentation. And I hope this has been of interest to you, and thank you for viewing.